Hello everyone, my name is Yu Mingrui. It's a great honor for me to present our work, Shape Control of Deformable Linear Objects with Offline and Online Learning of Local Linear Deformation Models. In this work, we consider the shape control of deformable linear objects, just like these previous works shown in the video. The task objective is to manipulate the DLO to the desired shape. For control, the key challenge is to obtain the exact deformation models. In other words, how the robot motion affects the DLO shape. The previous methods to obtain the deformation model can be summarized as follows. First, using analytical models. However, they are just approximate model and require accurate DLO parameters. As a result, data-driven methods are more practical. They can be further divided into offline and online methods. In offline methods, the most common one is to offline learn a nonlinear global forward kinematics model. However, the model training is usually data inefficient, and they may get into trouble when manipulating a new DLO. The online methods usually online update a local Jacobian metric. These methods can be applied on any new objects, but they are only effective in local configuration and less accurate. To address this issue, we propose a new method which learns the deformation model in a coupled offline and online manner. The model is first trained based on randomly collected data in the offline phase, then seamlessly migrated to the online phase as an initial estimation, and further updated while achieving the shape control tasks. The advantage is that it can allow for both more accurate modeling via offline learning and adaptation to new DLOs via online learning. As for the formulation of the deformation model, we use the local Jacobian in a global way. Here, our Jacobian model is not just a metric, but a mapping from the state to the Jacobian metric. The advantages are that it is both globally effective and more data efficient because it implies a strong linear prior. We proved the reasonability of this formulation under the quasi-static assumption. We use an RBFN to approximate the Jacobian model. We also propose a proper relative state representation as a network input. During the actual manipulation, the weight of the RBFN is further updated to compensate for offline modeling errors. We also analyze the stability of the closed-loop system using the Lyapunov method. We build both 2D and 3D simulation environment. The offline model is trained using only simulation data. First, we compare our Jacobian model with FKM. We test their offline model accuracy on a certain DLO. The results show that our model can achieve more accurate predictions with less training data. We also validate the proposed relative state input. The results show that it can enable the offline model to have better generalization ability on new DLO. Here we show some shape control results in the real world. It has shown that our method can achieve better shape control results than the previous works. Here are more cases accomplished using our method. In summary, our method is more stable and more precise. In conclusion, we propose a new scheme for shape control of DLOs, combining both offline and online model learning. We conduct both simulation and real-world experiments to show the superiority of our method. Recently, we have just submitted a journal version of this work in which we propose new model modifications and training strategies, a new optimization-based controller, a new robust online model updating law, and more detailed simulations and experiments such as dual-arm 2D shape control, dual-arm 3D shape control, some potential application cases, and a demo for obstacle avoidance. That's all. Thanks for listening.